Before we start the upcoming problems, let's quickly review what a first-order linear equation looks like. A first-order linear equation is one in which the highest power of the derivative is the first power. That corresponds to our first order. And the linear aspect is that our dependent variable, in this case our y and our derivative of y with respect to x, both of those are to the first power. And then what we'll see is we can have the right side fully in terms of x, our independent variable, and then some function of x getting multiplied by our y term. And the reason we want to recognize this is we have a very specific way of solving these first-order linear differential equations, and that's by using our integrating factor, which comes from taking the function of x that's getting multiplied by our y variable, and then integrating that in the exponent of e. And we'll see how to follow this through in the future steps in our next problem. So let's first see, does this fit our first order linear equation formatting? We see that we've got the right side fully in terms of x. We have the highest power of the derivative is the first, so that's our first order. And each of the terms that involve our y, our function y, our derivative of y, are all to the first power. So this definitely is a linear first order equation. So let's solve this through our steps to solve linear first order equations. The first step is to find our integrating factor. And we know that comes from finding the function being multiplied by our y term. In this case, it is -2. And then the integrating factor is e raised to the integral of that with respect to the independent variable. So for this problem, the integrating factor will be e to the -2x. Once you've found your integration factor, you then multiply the entire differential equation by that term. So we'll take this and multiply it by everything on the right side, and then take it again, multiply it by everything on the left side. And at this point, if we've done everything correctly, something very nice appears on our left side of the equation involving the derivative of y and y. We see that this is actually the result of product rule on the derivative of e to the -2x times y. So all of this is the result of the derivative with respect to x of this term. So in our next step, when we seek to integrate both sides with respect to x, something very nice happens on the left side, because the integral of the derivative is just the original function. So as I integrate both sides, integrating the derivative leaves me just with the original function. So the left side becomes e to the -2x times y, and the right side is the integral of this. And before we write that down, let's simplify this. Since we have the same base, we know that you can add the exponents. So e to the 2x minus 2x is e to the 0, e to the 0 is 1. So this simplifies and just is equal to 3. So on the right side, we're integrating 3 with respect to x. So we get e to the -2x times y equals 3x plus c. And now we do want to isolate and solve for y. So we're going to get y by itself. We see that it's currently being multiplied by e to the -2x. So we could divide both sides by e to the -2x. And remember, whenever you're dealing with negative exponents, if you're dividing by a negative exponent, that's the same thing as multiplying by the positive exponent. So this just becomes y is equal to 3x e to the -2x, or sorry, positive 2x. And I might rewrite that a little more efficiently as e to the 2x being multiplied by the entire 3x plus c term. Now we found the general solution to our differential equation. However, we did have an initial condition. So we need to see what is the value of c that fits this initial condition. So when x is 0, the result should be that y is 0. Now e to the 0 we know is 1, multiplying by 1 leaves it the same. So we end up with e times 3 to 0, which is 0, plus c c has to be equal to 0. And then our final equation is just our original, except when we add 0, it doesn't change anything. So we could write it as y equals e times 2x times 3x. Now as we start our next example, look at it and the form for first order linear equations and see if this, as it's currently written, fits into this format. So I would say as it's currently written, it does not fit, although we could algebraically manipulate it to make it so. To do so, we would need to distribute out this term and then move all the terms involving a y to the left side, making sure that our derivative term is left by itself, and then have remaining terms of x to the right. And we will do that in this video. But before we do all that algebraic manipulation, take a moment to look at it and see if there's anything that we've learned in the past that we could use to solve this differential equation. What we notice is our differential equation, we've got terms of x's and y's joined by multiplication solely. So we could separate and get terms involving x's to one side, terms involving y's to the other, and do a separable differential equation if we find that each side is integrable. So for practice, let's attempt this problem 2 times. Let's first find the general solution through our separable equation technique. Then once we've done that, let's algebraically manipulate it and find the solution again through the integration factor that comes up when we have our first order linear differential equation. And once we've got the general solution the second time, we can substitute to find our initial value. So we have our derivative term, 2y dx, and we will divide both sides by 1 minus y. And that leaves this expression. We know when we integrate both sides with respect to x, we've got our change of variables that occur, and we end up with 1 over 1 minus y dy equals the integral of cosine of x dx. Now we quickly recognize the left side. We could do natural log absolute value 1 minus y, equals, and then the integral of cosine would be sine. And one correction we need to make here, whenever we're integrating this, we know that as we took the derivative, we would have multiplied by -1. So I need to accommodate that here, and the integral is negative ln absolute value of 1 minus y. Now let's solve for y. We can distribute the divide both sides by -1. We know if we want to solve to get y by itself, we'll have e raised to the left side equals e raised to the right side. On the left side, it becomes 1 minus y equals e to the negative sine of x plus c. We can get y by itself. Y would then be equal to 1 minus e to the negative sine of x plus c. And if we wanted to at this point, we could plug in our initial condition to solve for what c is, and we would get our specific answer to this initial value problem. So that's a great solution. Just for practice, let's also attempt this problem by turning it into a clearly written first order linear equation. To do so, as we mentioned at the beginning, we need to distribute this cosine through, and then we want to group our terms where we have our y prime plus some function of x times y equal to some other function of x. So we get y prime equals cosine of x minus cosine of x times y when we distribute. And we'll want to bring this term over to the left side by adding it to both sides. And we get y prime plus cosine of x times y equals cosine of x. And then checking our notes, we see this is exactly in the proper format for a first order linear equation. So our term that will go in our integrating factor is this cosine of x being multiplied by the y. And we'll multiply both sides of the equation by our integrating factor. And we know if we've done this method correctly, we should be able to look at the terms involving our y, the left side in this equation, and it's representing the result of product rule for derivatives of our integrating factor, e to the sine of x, times y. So remember that this entire thing is just the result of product rule here. And the reason this is helpful to us is now when we begin to integrate both sides with respect to x, the left side, the integral of the derivative, is simply the original expression that we are taking the derivative of, and then we can integrate the right side as well. So as we integrate both sides with respect to x, the right side becomes simply our integrating factor times y, and the left side is this integral. Now, as we think about our integration techniques, we look here and we see this is a perfect example of u substitution. U is sine of x, du is cosine of x dx. The integral of e to the u is e to the u. So the right side becomes e to the sine of x plus c, and that was equal to e to sine of x times y. So we'll have our general equation when we solve for y. I can divide both sides by e to the sine of x. And what that happens is we have for the first term, e to the sine of x. So we would write this as just our 1 plus c times e to the negative sine of x if we want to write it outside of the quotient. So this term becomes 1 plus, and then we can rewrite this, c times e to the negative sine of x. Now let's use our initial value to substitute and see what value of c we should use. And let's do this in both of our forms of the general equation, and we'll see that they do become the exact same expression when we solve for c. So in this first case, I have 2 is equal to 1 plus c times e. Now, sine of pi is 0, so this just becomes e to the 0. E to the 0 is 1. So as we solve for c here, we get 2 is 1 plus c, so c is 1. And we get our equation 1 plus e to the negative sine of x. Substituting the same values for x and y here, we get 2 equals 1 minus e to the negative. Now, again here, sine of pi is 0, but here we need to watch out because it's 0 plus c. And really quick, let's back up just a little bit. I think it will make our algebra a bit easier if I rewrite the constant here. Instead of saying the exponential is this term plus this term, we know that we can rewrite exponentials by, instead of adding their exponents, rewrite it as the same base multiplied together. So let's do that in our next step before we substitute in for the initial condition. So we have 1 minus e to the negative sine of x times e to the negative c. And one thing I want to keep in mind as I'm looking at this expression, this e to the negative c, remember c is a constant that we don't know the value of yet, but e to the negative c is also a constant. So I can solve this expression and see what c is, but I could also see what e to the negative c should be in this case, because that's the multiplicative term that should go here in order to make our initial condition work out. So we substitute, we get 2 equals 1 minus e. Now we know sine of pi is 0, so that's e to the 0, which is 1, times e to the negative c. We get the expression 2 equals 1 minus e to the negative c. So whatever this e to the minus c is, we know the only way you're going to get 1 here is if this whole term equals negative 1, because 1 minus negative 1 is 2. So that tells us this entire e to the negative c term is negative 1. I don't have to solve specifically for c in this case because this can be substituted exactly here. So our equation would be 1 minus negative 1 times this becomes y equals 1 plus e to the negative sine of x. And we see whether we solved using our separation of variables method or our integrating factor method, if we've done it correctly, we should end up with the exact same looking answer. So for this problem, it just comes down to preference, which method you would prefer to use. Now looking at our next example, we see that it is looking somewhat similar to this, but there's a few things that we need to fix to make it fit this procedure exactly. The y prime term needs to be completely by itself, and currently it's being multiplied by x squared plus 4. And we have our y term also on the same side, so that's fine. But we do need to get the y prime by itself, so we'll divide everything by this x squared plus 4. And that will give us this expression, which is in the proper form. We see the term that needs to be a part of our integrating factor, so we do that off to the side. And we see this integral can be well done with u substitution. So this becomes the integral e to the integral of 3/2 du over u, which will be e to the 3/2 times ln of u, and in our case ln of u is x squared plus 4. X squared plus 4 is always positive, so we don't have to use a customary ln absolute value of x squared plus 4. It's always going to be positive, so we can just drop the absolute values here. And I think what we'll find useful is, although we could still do the work with our integrating factor just like this, not simplified, it will complicate things a bit. So since we see that we could raise this constant multiple by properties of logarithms to the exponent, then we would have e raised to ln of an expression, and there we have the composition of inverse functions, and our integrating factor would simplify significantly. So let's follow through with that. We have e raised to the natural log of x squared plus 4 raised to the 3/2 powers. Remember, for logarithms, constant multiples become exponents. Composition of inverse functions, this just simplifies to our input. And that's the integrating factor that we can use for this problem when simplified. We know at this point we will multiply the integrating factor throughout the entire equation. Now here, before we go forward with integrating both sides with respect to x, I think we'll benefit from algebraically simplifying this term and this term. We've got the exact same base raised to exponents being divided. We know we subtract the exponents at that point. So x squared plus 4 to the 3/2 minus 1 will leave us with a positive 1/2. And we have the similar simplification on the right side as well. And now at this point, we can see the left side is the result of product rule. So when we integrate the left side and the right side, the left side just becomes the two functions that were being multiplied together that we originally took the derivative of, and the right side becomes the integral of that with respect to x. And of course, there was this y prime being multiplied by that first term. Now, as we work to integrate the right side, we see we can use u substitution here. We use our interior x squared plus 4. du would then be 2x dx. Now we just have an x dx, so we can multiply through by 1/2, and we get 1/2 du equals x dx. So as we simplify that, that's 1/2 u to the 1/2 du. And as we integrate that, we add 1 to the power and divide by it, so we get 1/2 times 2/3 times u to the 3/2, all plus our constant of integration c was originally equal to the right side. We have some simplification of the constants, and then we know u was our original x squared plus 4. And here, as we solve for y, we have a similar case as before. We're actually dividing by a term that exactly appears on the right side, so we know when we divide it through the equation, it divides out from here perfectly, and then we're left with c over that term, which is just c to that term to the negative exponent. So this will simplify to be y equals 1/3 plus c times x squared plus 4 to the negative 3/2. We were giving an initial condition, so let's substitute and solve for what c should be. So we substitute in 0 for our x squared, and we get 0 squared plus 4 to the negative 3/2 times c is equal to 1, and 1/3 added to that. So 4 to the negative 3/2 power, we know the square root of 4 is 2, cubed is 8, but to the negative power would be 1/8. So we have, subtracting the 1/3 as well, we get 2/3 equals to c to the 1/8 power. Multiplying both sides by 8, c becomes 16/3, and our final equation would be and one typo or one error as I copied it down, there does need to be a negative in our exponent, as we saw. That error needs to be corrected. Consider a reservoir with a volume of 8 billion cubic feet and an initial pollutant concentration of 0.25%. There is a daily inflow of 500 million cubic feet of water with pollutant concentration at 0.05% and an equal daily outflow of the well-mixed water in the reservoir. How long will it take to reduce the pollutant concentration in the reservoir to 0.10%? So let's first label some variables, maybe translate some of our expressions. I have things in terms of million cubic feet and billions. I'm first going to rewrite the 8 billion as 8,000 million cubic feet. So that'll just be a reminder to us later on, 8 billion cubic feet is equal to 8,000 million cubic feet. So we're working with the same units. And then let's let x of t be the amount of pollutant in the tank measured in our million cubic feet after t days. Because we know the amount of pollutant in the tank is varying as time passes because we are adding in a different concentration of pollutant and we're also outflowing some of the material in the tank. So the rate at which the concentration of pollutant is changing, the rate at which the amount of pollution is changing in the tank per day is related to the amount of pollutant that's coming into the tank minus the amount of the pollutant that's coming out of the tank. So dx dt equals rate in minus rate out. I think it's always helpful to start here. This tells us this is the general structure of the equation. And now we just need to carefully think through, okay, how can I express the rate of the amount of pollutants coming into the tank and then subtract that from the rate of pollutants going out of the tank. Now, as we think about this problem, one piece of it is simpler to understand. We know exactly how much water is coming into the reservoir and exactly the pollutant concentration. That's fixed. Specifically, looking back at the problem, we see that we are inflowing 500 million cubic feet, and the concentration of the inflow is 0.05%. So we can actually calculate the exact amount of water flowing in to the tank, and then, based on the percentage, find the pollutant concentration. So we have our 500 million cubic feet, and then to find of that, that's the entire amount of water and the pollutant that's coming in. Only 0.05% of that is actually the pollutant. So we can multiply by turning our percentage to a decimal, moving the decimal place over twice, multiply by 0.0005. So that's our rate in. Now our rate out, we know that we're having exactly an equal outflow, so we still have 500 million cubic feet flowing out each day. However, we don't know the pollutant concentration right off the bat because remember that's the mixed vat or the vat mixed reservoir. Coming in, we knew exactly what was coming in, but coming out, the percentages are not as clear. So, in fact, the percentage is changing based on how many days are passing because we are diluting it over time. So, we know the amount that's coming out, that's 500, but we need to figure out what's the pollutant concentration. Okay, and we're doing the exact same thing in both pieces. It's just here, we knew the amount in like we did here, and we knew the concentration because they told us. However, since the concentration that's coming out is a bit more complicated, for right now we're going to write this as our placeholder, and then we'll focus on how do we find the concentration that's coming out of the tank. Now, the way we think about the concentration is it is going to be the total amount of pollutants in the tank divided by the volume in the tank at T days. Now, the amount of the pollutant in the tank after T days, we know that's a variable amount. And specifically, we've labeled that earlier in the problem as our x of t. So the numerator becomes x of t, or our function x that depends on time. We can just leave it as x if we prefer. And now let's think about the volume. Initially, there were 8,000 million cubic feet. And each day that passes, we have 500 million cubic feet going in and the same amount going out. So since we have the exact same amount going in and going out, the total volume stays stable no matter how many days pass. We still have 8,000 million cubic feet each day. So in this problem, our volume is stable at 8,000. But now we've expressed the pollutant concentration, and we have our formula dx dt equals 0.25 when simplified minus 500 times x over 8,000. So at this point, we've finished with this setup. All we need to do to finish this problem is solve the differential equation, and we notice this is, or can be moved into a first order linear differential equation. Then we can use our integrating factor, and we will need to come back and solve our initial conditions to be able to find exactly when the concentration is 0.1%. So let's begin by solving the differential equation. Add this term to both sides. Now as we add this over, 500 divided by 8,000 simplifies to 1 over 16. X equals 0.25. We see our term that will join with our integrating factor, so we have our integrating factor is e to the 1/16 x. And out of habit, I wrote x, but of course our input variable is t, so this should be e to the 1/16 t. Because we calculate our integrating factor in terms of the independent variable. Multiply that by both sides of the equation. We see the left side is our characteristic result of product rule. So when we integrate both sides, the left side just becomes the original function multiplication that we were taking the derivative of, and the right side is something we can easily integrate. And we know this integral is 16e to the 1/16 plus our constant of integration. We'll simplify our constants, and that will be a 4. Divide both sides by e to the 1/16 t, and we end up with the amount of pollutants x equals 4 plus c to the e times negative 1/16 t when we divide both sides by e to the 1/16 t. Now, in order for us to find when the concentration was 0.10%, we need to have solve for our constant of integration c, or plugging in an initial value to find that. So we reread through the problem and we try to find, okay, where do we have an initial value that we can use? In terms of the concentration, we need to know at some time, some days, we know the concentration and we can find the exact amount of pollutants inside the reservoir. Reading through the problem, the only information of that type is when they tell us at the beginning we had 8 billion cubic feet of water plus pollutants in the reservoir, and the concentration of the reservoir at that point at the beginning was 0.25%. So we could find the initial amount if we take the 0.25%, write it as a decimal, 0.0025, multiply it by our 8,000 million cubic feet, and that should give us 20. So we have our initial condition of 0, 20. If we substitute that in, we can solve for c. 20 equals 4 plus c. E to the negative 1/16 times 0 is e to the 0, which is 1. So that's just times c, or times 1, which is c. Solve for this, c should be 16. Now at this point we have our specific solution to the differential equation. We still need to finish the problem by solving to see, okay, when, how long, so what t day, will the concentration be 0.1%? Take a moment to think about how we'll finish this problem. We're looking for at what day is the amount 0.1% of the total volume is pollutant. So similar to before, to find the amount, we actually need to figure out, okay, what's the volume in the tank? We know that no matter what day we're on, the volume is 8,000 million cubic feet because we have the exact amount coming in as coming out. Now, of that 8,000 million cubic feet, we want 0.1% to be the pollutant. So we have 0.001 times our 8,000. So we want the amount of pollutant to be exactly 8. So we're trying to solve for what t value gives us the x value of 8. So we have our 8 equals 4 plus 16 e to the negative 1/16, and our t value is unknown. We can solve for this, subtract 4 from both sides. You get 4 equals 16 e to the negative 1/16 t. Divide both sides by 16th, and we get 1/4 equals e to the negative 1/16 t. Natural log of both sides, natural log of 1/4 is negative 1/16 t. So we're almost at the final point. T will then be exactly natural log of 1/4 divided by negative 1/16, and we can round that to 22.2 days when rounded to a single decimal place.